Recording is in progress. I'm assuming my sound is good. Somebody let me know if they can't hear me. All right. Why is okay. So I'm going to start as always with the main page, and I have added a line here for you to submit issues or feature requests from basic graphics. So if you have problems or anything, you can submit it there. Just an FYI, and hopefully I will see it. Then we go to the schedule, and today we are on the 24th of March, if you can believe that. We are looking at data structures. Any questions on where we are? All right, no questions. So we go back here. We go up to this slide deck, and we move forward until we reach data structures. Now, this is just a reminder of the various, things that we're considering: iterator, iterable. We're going to talk about some linked list and map implementations. This was an iterator example I showed you. We talked about lists because one of the difficulties with lists, the java.util.list interface, and some of you still don't realize that's an interface, but it is. Java.util.list has too many methods on it for us to reasonably implement. So we have our own way of doing this. Now, my array list is, I'm not going to show you that because we spent a lot of time on that in the beginning of the course, but I can go back if there are questions. And the thing that was new there, I did show you, was the iterator. Okay, so let's look at the linked list. So a linked list is, instead of having a big array with everything in it, we're going to have a next pointer that takes us to the next thing. And the way that we do that is we make a class called a link or a node or something like that. And it has some object to store the data in this element of the list, and it has a link to the next pointer. And this static class in here is going to be the basic tool for this. This is going to be each link in our linked list. In addition, the main class has a link head and a link tail. At least this implementation does. There's like a billion different variations on the way you can do a linked list. And I'm also tracking the size of the list independently. Now, I don't need to do this. I could just calculate it whenever I want it, but I think it's kind of convenient to have it initialized. So the first method, and if you can get this, you can get everything there is to know about linked lists, really, is the get method. Now, in an array list, a get method is very simple. You just look up the item in an array, and you're done. But in a linked list, you actually have to do a computation. And the way this works is, first, you create some variable. I usually call it x. Link x equals head. So you initialize. So you have to remember here at this point that variables in Java for objects are not the object. They're a reference to the object. And my favorite sort of Chinese phrase is, the finger pointing at the moon is not the moon, right? So the x is a thing that's pointing to what the x variable actually has is it has the address of the memory in data where the link is stored. So I'm going to initialize x with that address, right? That pointer to the data. And then I'm going to say for counter equals 0, counter less than n, counter plus plus. This is a very standard thing. I'm counting up to n, right? I'm going to say x equal x dot next. So the next field in the link is another pointer to an object, right? And so I'm just walking through the chain down until I get to the nth item. And then I return x dot data. Does that make sense? One person thinks it makes sense. I have succeeded. It's walking one step further along the index. Right. You have to walk through the thing instead of plugging it in. All right, so let's look at the set method. The set method looks kind of the same. I have an object O, and I'm going to have this, all this part is exactly the same. The only thing that differs is the last line. Instead of returning x.data, I set x.data equal to O, right? So that's the get and the set method. The clear method is going to set the head equal to the tail equal to null, and the size equal to 0. Insert, now it starts to get a little tricky, right? Because we've got this link of things pointing next to next, and we want to put something inside it. So we have a list, say A, B, D, E, like the one I've drawn in ASCII text there. And I have a head. The head pointer is pointing to A. And the tail pointer is pointing to the end, the E at the end of the list. And so I'm going to set pos equal to 2. Now pos, what that should point to is this second element. It doesn't yet. It's just a number. It just tells you where that thing is, but that's the concept of it. And I want to insert something there. So so when pos is equal to 2 and x is equal to b, I'm going to say c points to d. So the link that I have, let's back up a little. At the top of the insert method, I instantiated the link object with the data that I wanted to insert, right? And then I went through a for loop and I counted to the position I wanted. So this x is now pointing to the position that I want to do the insert. So I'm going to say the link.next is the x.next. So this new link that I've created is now going to point forward to this d. And then I'm going to say my data item, which is b, which is going to point forward to that c. So that's x.next equals link. All right. If you can follow all that, you're in good shape. If you can't follow that, then you need to stop me and ask questions because you'll just get lost. Yes. Matthew? Michael. I had the M. All right. So there's a picture here, right? So let's take a look at this whole thing. I want to insert a position pos. I want to put object O. And for sake of an example, I want that position to be 2 and that object to be C. All right. So what I'm going to do is I'm going to create a new link object because I need to have a link object to hold every piece of data. And then I'm going to initialize X, another link object, another link variable X to be head. And then I'm going to count through the number of positions until I get to the one I want. I'm going to say 0 to pos minus 1. So that will take me to the one I want to be right before. I want to be right before the one I want where I want to insert. And then, well, I skipped over this part last time. So if the head is equal to the tail, right, that means the list is empty. And all I have to do is set the head equal to the tail equal to the link, and I'm done, right? That's it. There's nothing else I need to do. And I just noticed a bug in this code. Okay, well, we'll get back to that. So I set the head equal to the tail equal to the link. Now, if the head and tail are not null, right, then I'm going to do this other thing. So I'm going to say, for the sake of example, I have this linked list that goes A, B, D, E. And the head is A, and the tail is E. And the place I want to insert the new element is where that D is. And so I've got my X pointing to D, right? I mean, I've got my X pointing to B, rather. And so what I'm going to do is I'm going to say that this new element C, this new link C, is going to point, I'm going to fill in its next pointer so that it points to this D up here. So that's link.next equal x.next. All right. So X is equal to B, x.next is equal to D. This makes link.next point to x.next. C. It makes the C point to the D. Make sense? All right. Then we want the B to the point to the C. So we take x.next and we make it equal to the link. So now X.next, which is B, points to the link, which is C. The link.next points to D. And I've inserted that into the chain A, B, C, D, E. Make sense? Now, the thing I forgot to do here is increment the size counter that I was keeping. So I'll have to somehow, at some point, I'll have to go back and do that. But I clearly forgot to do that here. Anyway, that's the insert method. And I'm hoping my little my graphic here will help you understand that. Any questions? Yes, Vanik. Link.next. Okay, so link is the data element in link is pointing to B, right? Or I'm sorry, the data element in link is pointing to C, right? That's the one that we're inserting. Okay. So now on that link, I have to point to something that's next. Now that X is pointing to element B, right? So the X.next is going to be pointing to D, right? So I want the C to point to the D.
So if somebody can print.
Somebody is talking. I can't quite hear you. Somebody say something on the Zoom.
Hello.
Blah, blah, blah.
All right. My headset is just not working right. And yeah, okay. All right. So the next thing I want to do is an add. Now, this time I remembered to do the size plus plus. I should have put that on the insert as well, but I guess I just forgot. And what I'm going to do the same thing I did with the insert, right? I'm going to say link equal new link. I'm going to say if the head is null, I'm going to say the head is equal to the link. Otherwise, I'm going to say link X is equal to the head. I'm going to go through until I get to the end of the link. Well, okay, there's two ways I'm going to do this. One way is with the tail and one way is without the tail. So if I don't have the tail, if I didn't have the tail, this is how I would do it, the stuff that's commented out. But with the tail, I can do an optimization. So if head is equal to null, I can say head is equal to tail is equal to the link. Otherwise, what I can do is, let's say I have A, B, C, right? And I have the head pointing to A and the tail pointing to C. I can say tail.next equals the link. And then I can say, and that means that I now have this picture. I have A, B, C, D with the head at A and the tail still pointing at C. But what I can do is I can say tail equal link. And now I get this whole thing. So if I have the tail pointer, right, I can do these two steps to put something at the end, right? I have to first use the tail pointer to put it directly at the end. And then I use the tail point, and then I update the tail pointer itself. Just these two steps. If I don't, right, then every time I have to sort of calculate a tail pointer by starting at the head, looping until X.next is null, right? X.next equal null is going to be another way to define the end of the list. Yes, Matthew. Well, even if I have the size, I still have to walk through the list to get to the end, right? So having the tail pointer gets me out of walking the list when I want to do an add. Yes, Vanik. Well, I mean, I declared a variable, a field variable on the class called tail. If I didn't declare it, then I wouldn't have it. So it's two choices on how you can implement this. All right. And then the size is going to return the size field variable. And then I have a prepend method, which puts things on the front. Now, you may recall with my array list, right? I had to work really hard to do a prepend. I have to move everything. I have to copy everything over. But what I can do here is I can say, I can create this new object, this new link with this value, and its next pointer is going to be the head. So I have a constructor which initializes the next pointer on the list. So now I have temp, and temp is pointing to head. If the head is equal to the null, if the head is equal to null, then the tail becomes temp. Otherwise, the head becomes temp, and the tail pointer is going to be pointing to the head, and it's still pointing to the head. And then I do a size plus plus. Does that make sense? So all I have to do, right, is if I'm inserting into the front of a linked list, it's very cheap. It's order one operation. So that's an advantage that a linked list has over a regular list. But you know, depends on what you're doing with a list as to what is the easiest thing. Okay, so any questions? All right, so if I'm implementing a stack, right, something like this linked list is going to be one of the easiest things I can do, right? Because I can shove things on and off the front, and it's always order one cost. Now there are ways you can play games to make arrays more efficient, but there's always ways to do something differently. So any questions about linked lists? Vanik. Yes. Okay, let's go back to insert. Insert is one of the hardest ones. You just want to look at it, or you want me to talk about it? Right. So again, what we're doing, we always start by allocating a new link. Then we have to find our place that we're going to do our insert. So we create a temporary variable x, and we increment to the counter to pos -1. We want to point to 1 before the place we want to insert at. And then we do x equal x dot next to walk ourselves forward. If the head is equal to the null, then it's easy. We set the head equal to the tail equal to the link, and we're done. If we've got something more like this, A, B, C, D, E, then what I'm going to do is I'm going to have my pointer x is sitting at B. And so I want to say, and my new thing has a C in it. So I want C dot next to point to D, and I want B dot next to point to C. And if link dot next is equal to null, then I want tail equal to link, right? So that's in case I'm inserting at the end of the list. Make sense? Okay. Doubly linked list. Okay. So a doubly linked list is kind of like a singly linked list. The major difference between a doubly linked list and a singly linked list is that instead of just having a next pointer that takes you from the head to the tail, we have a prev pointer that takes you from the tail back to the head. So that means we have more bookkeeping to do. But if we want to move back and forth in this list, it's easier. Okay, so this time I called it entry instead of link, and I'm going to have head and tail, and I'm initialize them both to null. And I have a method called pushback, which is going to, and this is going to be, and unlike the last one, so the last one I had a generic list where I had just object as the data type. And in this one, I'm going to have int as the data type. I don't know, just a choice I made. Okay. So this pushback, what we're going to do is we're going to create a new entry. We're going to set the data. If the head is equal to null, then we're going to do what we did before. Head equal tail equal E, and we're done. Okay. Otherwise, let's assume that we have A, B, C with the A dot next is pointing to B, B dot next is pointing to C, C dot prev is pointing to B dot prev is pointing to A. And I have tail pointing to C. and head pointing to A. So I'm going to say tail.next is equal to E. Okay, so I'm pushing something onto the end. That part is easy, hopefully. Okay, and now I have this picture, right? So now I need to have E.prev point to C because that's missing. So I'm going to say E.prev is equal to tail, right? So tail is the last element in the list and E is the new last element. So I'm going to say E.prev is equal to tail. And now I'm going to update the tail to be equal to E and I'm done. So that took 1, 2, 3 steps to add something to the end of a doubly linked list. Yes, Matthew. Michael, sorry. I could have sworn I said Michael. Anyway. I'm sorry, what's the question? Yes. No, it isn't. No, it isn't. E.prev is null. Until I said it, it's null. E.prev, I mean, just see, this is a problem that you have making a transition from being a normal person to being a programmer, right? Is you think that things that are obvious to you are obvious to the machine. And that's just not how it works. You have to initialize prev. It doesn't know. So I had to say, I had to tell it what next was, but that didn't tell it anything about prev. It has no notion of what I'm trying to do. Unless it's AI, and then maybe it does, but AI will be the death of us all. Okay. All right. Any other questions on this? All right. Pop back. So this is gonna be like a pop method. So we're gonna take something off the end. And the way we're gonna do this is we're gonna imagine we have a list that looks something like ABC with the backward pointers filled in, right? And the tail pointing to C. So I'm gonna say entry C is equal to tail. And then I'm gonna say tail equal tail.prev. So I've moved the tail back already. It now points to B. And so now I have this picture here, ABC, CBA, and tail points to B. I'm going to set tail.next equal to null. So what I'm doing is I'm snipping this pointer from B to C. Okay. And that's actually all I need to do. I don't need to null out the C.prev pointer because C is gone, right? It's dead and gone. The Java garbage collector will clean it up. That part the computer does know. And then I return C.data, which is the data element that I popped off the stack, off the doubly linked list. So to pop back, I needed to do two things, right? I needed to do 2 things to make it happen. I had to move the tail pointer, and I had to set the tail.next to null. But that's all I had to do. Make sense? Bannock. So in this method, you're returning the integer that. Yes, I'm returning the integer that I popped off. Okay, so now I'm going to push something onto the front of my doubly linked list. So I do everything kind of the same, right? A new entry, E.data equal V. If head is equal to null, then head tail equal V. But else, okay, I say head.prev is going to be E, that new thing that I created. And E.next is going to be head. Okay. So I've made E sit in front of head, and I've filled in both links. And now I've now I update head to equal E. Make sense? For a lot of students, they've struggled with the notion that a variable is a reference and not the object itself somehow. And it's once you get to linked lists that you're really forced to confront, really forced to understand that a variable is a reference, that you can have multiple references to the same thing and they're not copies. They're not copies of that thing. They're just copies of the reference to the thing. All right. Let's look at pop front. So we've got ABC with the pointers. We've got the head and tail. First thing we're going to do is we're going to move the head so that head.next, instead of pointing to A, points to B. Okay. And now what we're going to say is head.prev is null, and we're done, right? We've cut off the head of the list, and we can return A.data. It's just like the other method, except we sort of, swapped head for tail and prev for next. So we can push and pop on either end of a doubly linked list with ease. Okay, so we should have iterators on our lists. And the nice thing about iterators is they have roughly the same performance if you're going through a linked list as you're going through an array list, right? Because in each step, you're going through one by one. And so I have an int iterator called forward, and I'm going to return an int iterator. By the way, is an interface I just made up, right? It's like iterator, but it has an integer as its data type. And I'm going to say, and let's see, I think I should go look. I probably have where do I have int iterator linked? I don't have it linked. Well, that's not very nice of me, is it? Let's find it. Give me just a minute. I need to add this to the slides. So int iterator, it's just, shoot. You love how they've designed these interfaces. So you have to hit precisely this one little thing. And if you grip slightly wrong, it just goes to the click on the thing behind it. So convenient. Interfaces are really, as you're finding out if you're doing basic graphics, doing any kind of graphical interface is really hard. One of the things that the discoveries I made recently is how hard it is for an older person to use a phone, right? You think, oh, it's easy, right? You just click on the things you want to do. And what could be easier than that? And then I watched this woman in her 80s, right? You hand her the phone and she like grips it like this. And her fingers touch the edge of the screen and the phone jumps all over the place because you touch the edge of the screen, and it interprets that in various ways. So it took her like 3 tries to figure out how to hold the phone without touching the screen at all. And then she goes to, her finger is shaking and she goes to touch the name of the person she wants to call. And the phone says, if that's a swipe. And it just goes off and does some other crazy thing. And it didn't occur to me before, but if you've got any kind of difficulty using your hands, this thing is a nightmare. Anyway, so that's a detour. So my iterator is just like the iterator interface. The only real difference is it returns an int instead of an object, and you can't use angle brackets with it. It's just a little simpler. And I should have had it there. And that's not where I want to be. That's where I want to be. Okay, so I'm going to create a new int iterator, and I'm going to override the 2 methods on it. I'm going to have has next, and I'm going to have next. And what I'm going to do is I'm going to put a field on my int iterator named E, and I'm going to instantiate it with entry head and null. So this is going to be the, let's look at the constructor for entry. Constructor has a next and a previous value that you can give it. And it also has an empty constructor, which will leave those both null. So what I'm doing here is I'm setting the head to be the previous pointer, and I'm setting the next to nothing, right? So the way this link is positioned, right? I'm sorry, its next pointer is the head. So it's positioned itself sort of pointing at the head as its next pointer. And I'm going to return e.next not equal to null to determine if there is a next, right? So in a way, if you think it's like before the next pointer, before the head pointer. And then if I want to do a next, I'm going to say equal e.next return data, return e.data. So that allows me to iterate over a list. It won't die with a null pointer exception if I have an empty list. And if it's got one thing in the list, it'll return me that one thing, and it'll go forwards through the list, right? Does that make sense? All right. Now, backward, basically what we do when we want something to go backward, we just sort of reverse everything. We reverse head with tail, we reverse next with prev, and it all sort of works in the reversed way. So in this case, I'm going to say entry E equals new entry. And this time the next pointer is going to be null, but the previous pointer is going to be the tail. So it's going to be after the end of the list pointing at the tail. And my has next is going to look at e.prev instead of e.next. And if e.prev is not null, then I have another element. And if I want to get that element, I say e equal e.prev and return e.data, right? And that's how that works. Make sense? Yes, Vanik. Yeah, so if you look at the entry, right, the entry class, we have a next and a prev inside entry. And we have two ways to instantiate the class. We have an empty constructor, which will leave next and stop doing that. Next and prev both null. And then we have another one where you can supply both the next and the prev, and it just gets copied in. Okay? Any other questions? All right. And then I have a main method. We should try running this. Actually, I think if I just go. Yeah, all right. So here's the class right here. So I can just say Java dub link. Okay, and that says 012210. Is that what it should say? Let's go look at it again. So we create a doubly linked list. We push back 1, we push back 2, we push back 0, right? Then we do an int iterator, and we say dl.forward. So we should get 1, 2, 0, right? And then backwards, we should get 0, 2, 1. Make sense? Good. Now you understand everything about linked lists. You have crossed another threshold in your life. Achievement unlocked. I should start saying that more often. All right. All right, so that's linked lists. We've got singly linked lists, we've got doubly linked lists, and we've got our time complexities spelled out for us. Now let's go back to talking about the map again. You remember the map? Find the map, find the map, find the map. Okay. So we showed how to make an array map, right? Why is my computer slow? All right, so we looked at my array map before, and we can use either a linked list or an array list to implement it. It kind of doesn't matter, right? Both of those implement the list interface. And if I want to switch one for the other, it's as simple as changing this one line of code. Now, if I wanted to do a get, I walk through the list using an enhanced for loop, and that works with either type of list. And I just look for the key that I want to have, right? Because I have these entries, and these entries have a key and a value in them, right? You remember that? Does all look familiar? All right. And then the only thing that's different about these is, in this case, I return a value. In this case, I set a value, or I add a new entry to the list, okay? So this is all, very simple, straightforward code because, there's just not a lot of logic here. There's some logic to doing the iterators, and but we found out that all the iterators were basically the same, right? Once you figured out how to write the key iterator, then you could get the value iterator by just replacing the K with a V. And you could get the entry iterator by replacing the E.K with an E, right? That's all there really was to it. All right, that all sound familiar? Any questions? All right. Now, the array list this array list map, this array map thing works, and working is a great property for a code to have. However, it's highly inefficient. It's kind of like if you are searching for a library book in the library, and your library has no organization at all. It just has a big pile of books, and you have to go through every one until you find the one that you want. Computers are fast. They don't mind doing this kind of thing, but you might mind waiting for them. And, depending on the size of the number of books in the library, that may be acceptable or not. What you would prefer is to organize this list organize this map more like your library, and have a hash key that allows you to look up by author's name. So the 3 letters of the Dewey Decimal System are a hash key, and we want to emulate that. So a hash code. So my hash map. Let's take a look at our hash map. Now, I did this 2 ways, I guess. I could have done this slightly differently. All right, so there's 2 different ways of doing hash maps, and I sort of, in my mind, it's the good way and the bad way. So I'm going to show you the good way. But the idea is, I'm going to think of this thing as having buckets, right? Each of my combinations of 3 letters of the author's last name kind of thing is a bucket that I can store things in. And a bucket is a list of entry objects. And my collection of buckets is a list of lists of entry objects, okay? So what I'm going to do, I have a compute size method, right? Where what I'm going to do is I'm going to go through, and the way it's going to work, I'm going to take this variable C, initialize it to 0, and then I'm going to look at all my buckets and add up the size of all the buckets. And that will compute the size of my hash map. Okay. My hash maps need to have a size. When I create a hash map, I need to know how many buckets I'm going to have. I mean, it's possible to change the number of buckets later, but it involves reshuffling and it's work. So what I'm going to do is I'm going to initialize it with some number of buckets n. And if you don't want to figure out the number of buckets, I'm going to default to 100. Okay, just an arbitrary number I picked. And so what I'm going to do is I'm going to say, while the buckets.size is less than n, I'm just going to say buckets.add new array list, and that will get my number of buckets up to the correct number. Any questions? All right, good. Okay, so now I'm going to create this member function called hash. And what it's going to do is it's going to get, first thing it's going to do is it's going to ask the key for its hash code, right? And then Now that key can be positive or negative because it's an integer. Then what I'm going to do is I'm going to take the absolute value of that hash code. And so now I have a positive integer. And next, I'm going to do a percent with buckets.size. So what I've done is I've taken that arbitrary integer that came back from hash code, and I've converted it into a valid index into my list of buckets. Okay, it's somewhat arbitrary, but that's fine. Arbitrary is actually kind of what we're going for here. So so if I create a good hash code, right, it will tend to split things up into the buckets nicely for me. So each bucket will be small. All right. So let's look at how the put and get objects change with this new version of doing hashes. So first, I'm going to say list entry HL. This is going to be a bucket. This HL is a bucket. It's a list of entries. And I'm going to find it by saying buckets.get and then hash and then key. So I'm going to take the key, this object key here, and I'm going to call it with hash, and that's going to return a bucket index, a valid bucket index for me. And now I'm going to go through the entries on that bucket. And this part looks the same as my array list, or my array map rather. This part is exactly the same as my array map. And well, this part is too, right? And I'm keeping track of size, so I do a size plus plus. So the only thing that's really different about this code and the array map code is this first line where I get a bucket based on the key. And that means that if I have 100 buckets, I've immediately cut down the number of things I need to search by a factor of 100 on this first line, in principle. Make sense? All right. Now my get is going to be, again, it's going to be similar. It's going to start with the same thing. I want to find which bucket I need to care about. And then I'm going to look at my entries in that bucket. And if I find it, I'm going to return it. And if I don't find it, I'm going to return null. Okay. I have a size method. I have an assert in here that says size equal compute size that checks that the size calculation is done correctly. I have a clear method. My clear method has to walk through the list of buckets and clear each one and then set the size equal to 0. And that's basically it. That's basically how I make a hash map. And so to test it out, I created a class called numval, and it's got a final int field, and I instantiate it with the constructor. I have an equals method on this class because anything that I want to use in a hash map has to have a valid equals method, right? And then I have to have a hash code, and I could put almost anything in here, but n is already an int, so I can just use it directly. And then I can have a toString method, which just converts the int to a string. Okay, so that's what numval looks like. And let's skip ahead to the main method. So I'm going to create my min map. We'll create a min map pointer with my hash map. And then I'm going to put 20 things in there. I'm going to print them out. And I'm going to, so what I'm doing is I put numval as the key, and I'm going to put I times I as the value. So this is going to be a map from a numval to an integer. Now, I'm just going to go point out that when I made my numval, right, when I made that key that I wanted to use, I made the int n, I made it final, right? If I don't make this final, I'm potentially asking for trouble. If I change that value of n while it's in a map, right, the map is going to be all messed up. It's going to have the wrong notion of the hash code. It's going to have the wrong notion of where it belongs, and it's just not going to work. So if I want to use something as a key, it better be something that I can't change, because if I rely on myself to remember not to change it, I'm probably going to screw up. Okay, So I'm putting things in here. I'm putting numval and the square. And then I'm going through and I'm printing it out. I'm printing I, I'm printing h.get, new numval I, and then I'm gonna print, and that should be I times I. And then I'm also gonna print I times I as a comparison. And then I'm gonna say for I in h.keys, I'm gonna print the key and the value. And then I'm gonna put hello world into my map. And then I'm going to iterate over everything in there and print the entries. Now, you're looking at this and you say, you put a string and a numval in the same map. Isn't that wonky? Yes, it is wonky. But you can do it because this doesn't have any notion of the type of the thing in the array. It's just an object. And so long as the equals method and the hash code work, it will work. Okay, so when I go to print this out, right, when I go to run this, I see 0, 1, 4, 9, 16, 25, and so on, as you'd expect, up to 20. Here I go from the keys to the values with my next iteration through, and it's fine. Then I iterate through my entries after adding the string, and you see all the numeric values as well as the string value. Yes.
So when it is a string value, it just doesn't, like, it knows.
It doesn't know what, it doesn't know that it's a string. All it knows is it's got hash code and equals, and they do the right thing. That's all it needs to know. Now, generally speaking, you want to be a little more organized this. You want to use a list for one type of thing. And with the built-in hash map, you can use the angle brackets to do that. But this class is more basic than that one. All right. I think that's enough for today. Any final questions? All right, you understand hash maps now. Achievement unlocked.